Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of SERDP and ESTCP by Mr. Tim Tétrault, followed by a list of upcoming webinars in the series. After Tim's opening remarks, we will transition to the technical portion of the webinar. Today's event focuses on Department of Defense research efforts on building envelope technologies. First, Dr. Rolf Nielsen of Argonne National Laboratory will present results from an ESTCP demonstration of SonicLQ Quantifier, a patent-pending device that uses sound waves to locate and quantify building envelope leakage. Rolf's presentation will be followed by a question and answer session. Next, Mr. Curtis Harrington of the Western Cooling Efficiency Center at the University of California at Davis will present results from demonstrations of a new automated aerosol sealing technology. We will conclude the webinar with a second question and answer session. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A sessions. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Mr. Timothy Tétrault, who is the ESTCP Program Manager for Energy and Water. Before joining SERDP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim?
Thank you, Rula, and welcome everybody to today's SERDP and ESTCP webinar. I'm going to go over a quick overview of the programs and then hand it back to Rula to get on with the presentation. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, Department of Energy, and EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs that are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale with occasional supporting lab efforts are conducted. There are 4 program areas in SERDP and 5 in ESTCP. Energy and water program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focused on research and demonstrations that were conducted under the Energy and Water program area. Energy and Water has essentially 3 main areas of research: smart and secure installation energy management, efficient integrated buildings and components, and distributed generation. Our webinar series will be highlighting research and demonstration efforts from each of the 5 program areas. We have one remaining webinar in December, and we'll resume the series in 2018 with a webinar roughly every 2 weeks. You can find more information about upcoming webinars at this link provided here. Registration is now live for webinars through the end of the year. And just a reminder that our SERDP and ESTCP symposium will be held at the end of this month in Washington, D.C. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration is still open, and registration as well as program information are available on the SERDP and ESTCP website. With that, I'll hand it back to you, Rula, and I hope you all enjoy the presentations today.
Great. Thank you so much, Tim. It is now my pleasure to introduce Ralph, who is a principal building scientist at Argonne National Laboratory and the inventor of the SonicLQ technology. At Argonne, he is the Building Energy Decision and Technology Research Section Leader in the Energy Systems Division, and also the lead of the lab-wide Urban Science and Engineering program. Ralph received a BS degree in Electrical and Computer Engineering from the University of Wisconsin-Madison and his doctorate degree in Acoustics from Penn State. He is a fellow of the Acoustical Society of America, an Institute of Noise Control Engineering Board Certified Noise Control Engineer, a licensed professional engineer, and a lead accredited professional. With that, I'd like to turn it over to you, Ralph.
Thank you, Rula. Thank you, Tim. I appreciate the opportunity to talk to the audience today. As Rula had mentioned, so I work at Argonne National Lab, and as Tim had mentioned, these these webinars are talking about demonstration projects. Our project, although it was awarded last year, is a little bit late in getting going, so we're not going to be able to show you results of the actual demonstration. That's going to be starting to take place in spring, but we will be able to talk about where this fits into the ESTCP and SERDP programs, the technology itself, as well as the testing plans that are going to be starting again in spring. So what the technology we're talking about, the SonicLQ, is you'll hear a little bit more about in a second, is a technique for measuring leaks in building envelopes, air leakage. The real need for a new technology has to come about from the fact that the Department of Defense has some very strict requirements for air leakage in new and existing buildings, especially with retrofits. Back in 2009, there was a directive in Engineering Construction Bulletin, ECB 2009-29, and a follow-up one in 2012 that put down very strict requirements for air tightness, and that worked along with this was a development of the U.S. Army Corps of Engineers, a USAC air leak testing protocol. And in those, there was a set of requirements for really strict limits on infiltration rates of buildings that are far below standard code within the U.S., both residential and commercial code, and even lower than some of the very strict requirements found in commercial buildings and residential buildings in Europe. So we have a technology that, or a need for a technology in order to be able to measure infiltration. Now there are existing methods, and the test protocols use blower doors, which is a very common way of doing measurement for air infiltration. That measures the whole building envelope air leakage rate, and then the use of infrared cameras or a few other technologies that will help you locate individual leaks. But the two things have to be used in conjunction to be able to find the size of the holes in the building and the overall air leakage, as well as locate where the leaks are. But there's some big limitations. In particular, the existing methods, blower doors and infrared cameras, can't be used during construction. So if you're building a building, you can't put on a blower door until you've sealed off all the walls. I have the walls and windows in, I have the roof on, I have all the windows in, and that means that you can't really do quality assurance, quality control using blower door. In existing buildings, if we have moved in and we're trying to do commissioning and do some testing, maybe after some sealing, it can be disruptive to operations. When you're using a blower door, people can't go in and out of the building. People can't be in the building using it. When you want to locate leaks using an infrared camera, you have to have a temperature difference between the inside and the outside of the building, and preferably more than 10 degrees Fahrenheit, which means the perfect time for doing this testing, the fall and spring, when it's comfortable outside temperature-wise, it's not too hot, not too cold, the temperature is not 10 degrees different from the inside of the building. So I have to turn on the heat really high or the air conditioning really low in order to be able to actually use an infrared camera. And then even when you have a camera that will locate where you might have air leaking out, you can't differentiate air leak easily from a thermal bridge. Maybe there's a piece of steel that connects the inside to the edge of the building envelope. So you have heat coming through that, as well as you can't actually say how big one leak is relative to another with any quantification. So the technology that we're talking about, SonicLQ, can overcome these and provide more information for base managers, facility managers to prioritize the sealing of leaks, or in construction to catch those leaks before you get to the final product and close up your walls. So the benefits to the Department of Energy can be really pretty large. Right now, if you look at the overall military installations on US, there is about 40 tera-BTUs that are wasted in heating and cooling, specifically due to infiltration, which is about $760 million a year. If we were able to reduce just 10% reduction of that wasted energy, corresponds to 40 tera-BTU and $76 million a year. That's an enormous payback for having a technology that lets you do easier, faster, more testing, either for existing buildings or improving the construction of new buildings going up. If you think about somebody who's trying to retrofit an existing military base, one of the limitations to doing retrofits is the amount of time it takes in order to be able to do the air leak testing and the windows of opportunity in which you can do them. If you are able to, with a new technology like SonicLQ, do more testing to be able to retrofit more of your buildings, it only takes an extra 10 tests a year and retrofits to those buildings and the energy savings associated with sealing those up to pay for the cost of actually buying a piece or a part of the equipment, the SonicLQ equipment, which we think will have a market cost of about $10,000. Slide 19. So,
please proceed, Ralph.
Okay, I am having a glitch here. I need to, there we go, slide 19. So, additionally, besides the energy saving benefits, there are some other benefits that are particular to the Department of Defense. In particular, the air leakage directives, the ECBs, not only called about the energy savings. There's the need to reduce vulnerability to CBR attacks. Anything here, if you have chemical weapons, biological weapons, radiological weapons, much of the danger comes in when this might be outside the building and leaking in through leaks in the building envelope. So anything you do for the energy purposes in sealing up the building is also going to help you have higher resistance to CBR attack. You also get benefits of better indoor air quality. If you seal up leaks in unconditioned air, problems that you might have, say, truck exhaust or other outside air conditions that would lead to bad air quality, you don't have to worry about those things coming in through the building envelope if it's well sealed up. Another benefit, especially for a lot of older buildings, is sealing up air leaks is going to reduce the amount of moisture that's going to be traveling through the building envelope, especially in places where you might have settling of and have condensation, which can give you moisture damage, whether it is a bubbling of the paint or the plaster, or even freeze-thaw problems that can happen in concrete and brick. Slide 20. So let me tell you how SonicLQ works. The basic technology is fairly straightforward, and it was derived from looking at how you can actually do testing of sound leakage in buildings for making sure that you've got good sound isolation of a building from the window envelope and wall envelope. So it starts out by having a loudspeaker that generates sound on the inside of the building. Slide 21. On the outside of the building, sound's going to come through the building envelope either through leaks or through vibration of the walls and windows. On the outside of the building, you use a microphone array, a digital microphone array that is going to pick up the sound on the outside. And you measure this at something at 10, 20, 30 seconds worth of data that you measure. Slide 22. That information from the digital microphone array is transmitted over to a computer tablet that uses the patent-pending algorithms to separate sound that comes from cracks and what comes from vibration of the wall. And then it computes the air leakage rate and the sizes of the cracks, and it actually creates a sonic picture of where the leaks are. And we can actually overlay that with a photograph that may have been taken with a camera attached to the array to get something like slide 23, where we would have a picture of the wall. We have a color-coded piece of information that looks a lot like what you get from an infrared camera showing you the leak locations, but that information is truly quantitative. I can look at the localized air leakage rate in terms of CFM per square feet, so that the final product I take acoustic and visual pictures of the outside of the building at a distance that we will see here in about 3 feet. And those pictures will give you the overall air leakage for that entire section that was under test, as well as locate and size the individual leaks. So you know where it is that you have to seal up and where it is that there may be a little bit of leakage, but it's not beyond the strict requirements. Slide 24. Now the benefits of a technology like SonicLQ are the ability to be able to do testing in any sort of building of any size. You think about on a military base where you have offices that might be 2-story, 3-story buildings, but can be very large in terms of the overall square footage. That would be too difficult or very onerous to try to do with a single blower door. So you would have to go into the building and seal off individual sections of the building and rooms. With SonicLQ, you roll a speaker into each of the rooms individually, and you go to the outside where you can take your acoustic pictures on a room-by-room basis. It's just as useful for doing things that are a little bit more residential in nature, like barracks. Slide 25. Because of the way it uses acoustics rather than having a large pressurization, you can use this in any phase of construction. You can use it while walls are being constructed as a quality assurance, quality control, so you know you're going to meet the strict testing protocol requirements of the USACE air leak testing protocol. You can do it on an existing building after it's been completed, even while it's being occupied. So when you want to do testing of a building that you're going to retrofit, to say, all right, how much might I be able to save in energy by reducing air leakage? You don't have to wait until that building is not in use. You don't have to come in and do testing in the middle of the night in an office. You don't have to wait till troops are out doing on maneuvers to be able to go do some of the residential barracks. You can do this while the building's occupied. Slide 26. Because we don't need a temperature difference between the inside and the outside in order to do that localization and the sizing, we can do this at any season of the year. You can do it spring, summer, fall, or winter. I don't have to have a temperature difference, so I don't have to worry about is it hot or cold outside. Slide 27. So the magic of how we're able to do this sort of testing comes about through the use of the digital microphone array and a technique called Nearfield acoustic holography. So the special sauce, if you want to talk about that from SonicLQ, is the digital microphone array, when you're close to the wall, is able to measure 2 different types of waves that are given off from vibration or air through cracks. Propagating waves, which are the normal ones people think about, that actually decay as 1 over R. The amplitude goes as 1 over R, and is the normal way that when you're hearing a sound far off, how the sound propagates. When you're really, really close to the source, though, there's another type of wave called evanescent. These decay exponentially, and it's not just related to the distance, it's also related to frequency. So low frequency sounds will have a longer decay distance than the higher frequency sounds. So if you have low frequency sounds like we use with SonicLQ and we're close to the wall, we can measure both propagating waves and the evanescent waves. And those two things together let us do a lot more computation, get more information about the sound, lets us actually do that separation of sound that's a crack from and a leak from sound that's coming through vibration. And actually, then we can compute the overall size of the leak. Slide 28. So when we're close to the wall, we have a very small sort of area of test. Typically, we will be using SonicLQ in the close mode about 3 feet away, which gives us a window, a picture window, acoustic window of about 3 foot by 3 foot. So if I was to try to go and map out an entire building doing 3 foot by 3 foot pictures, it would take a long time. But most of the building doesn't have leaks. So what you can do instead is actually move far away with the same microphone away, and you would do acoustic beamforming. So the beamforming of this array works just like microphone arrays on all kinds of things in the Department of Defense that actually do acoustic tracking. So I do a standard beamforming, so if I'm 20 feet away or 30 feet away, I can actually take a large acoustic picture, and with that picture I can see anywhere there's sound coming through the building envelope. I don't know if it's vibration or if it's a crack from the faraway picture, but I can say, oh, here are areas I don't have to test, and here are areas that there might be leakage through a crack or there could be leakage from vibration. I then go to those areas and I go up close and use a near-field acoustic holography to separate sound that's coming from crack and vibration. Slide 29. So for a few of the details of the acoustics that are actually involved, the frequency range at which we do the low frequency near field holography, the close-up measurements, is typically about 50 to 300 hertz. The frequency isn't just set to a single number. It will depend upon the background noise. If I have resonances in the building, that could become problematic. Is there something else that is limitation in terms of modal structure inside the building that wouldn't give me even pressure? So I don't pick an exact number, but it's at fairly low frequencies. The beamforming that I use to look for any overall leakage or vibration is typically done on a much higher frequency range. One of the questions that often comes up is, how loud is this? Do people have to have headphones on? Do we have to worry about noise-induced hearing loss? Because we're actually using single frequency tones, or in some instances we could use a chirped frequency response, that's a swept sinusoid, we can reject background noise without having to have really high sound levels. So typically inside we'd be using 60 to 75 dBA, and then outside we'll have something that's in the 40 to 70 dBA depending upon how big the leak is. So we don't have to have a situation where anybody actually has to worry about noise-induced hearing loss or wear any hearing protection. The special magic of the microphone array is something that has been used in industry, both the aircraft industry and automotive industry, this near-field holography, for a long time. But instruments are typically tens of thousands to hundreds of thousands of dollars just for the microphone array. We've been starting to use digital microphones, very similar to the ones that are found in cell phones, that are very low cost. They actually have built-in A to D converters, and we're able to put together a microphone array for hundreds to low thousands of dollars that we can use within SonicLQ that give us the performance that we need at a much lower cost than the standard near-field acoustic holography array, which lets us have an instrument that overall costs in the $5,000 to $10,000 range as soon as we add the portable speaker and the tablet and the software. I already mentioned that we have two sort of different measurements. Our beamforming, where we take that large picture from far away, is about 10 to 20 feet. And then when we're close up for the near-field acoustic holography that actually sizes and locates specifically, it's about 3 feet or less. And that gives us measurement areas that basically are related to distance. So I can do a 9 or 10 square feet of a near-field acoustic holography image at a time. So it's 10 to 20 seconds. I can do that 10 square foot of NEH. Whereas beamforming, I can be doing a 20 by 20 feet. I can do much of the wall of a residence from that one far-off snapshot. Slide 30. So far, as I said, we haven't started our ESTCP program. We've been doing field validation at Argonne National Lab. You can see a picture here that's actually within a vestibule that has a crack. On the left, we can see this crack that's running down between cinder blocks. When we're at a distance of 8 feet away at the far edge of the vestibule, you can see on the very top right picture what you get from a beamformer. It's like, okay, I can see that there's sound coming off there. Way on the left, actually, you can see reflections within the building that you might say, oh, is that really a crack or not? If you were outside, we can go ahead and do the near-field testing and see that the little image on the left, the little red, is not a crack. Whereas the image on the right, when we do our close-up testing, we can actually see the crack mapped out. This is a typical picture that you might get from the near-field acoustic holography. And the size of those, it's the intensity that gives you, the color intensity. It will tell you something related to leakage. Slide 31. So the demonstration project that we're going to be starting here in a couple months is going to be comparing SonicLQ to a standard blower door and IR test. And we're going to be doing it at Fort Leavenworth and Hill Air Force Base. We're going to be very soon going out to select exactly which buildings, work with the building managers out there to select some typical buildings and actually ask them, what are the types of buildings that you would see give you the most problems in terms of whether it's timing or difficulty in doing your measurement, so we can see what they would like to best use the SonicLQ technology. And what we're going to be doing here is comparing the accuracy, the time of testing, the ease of use, and then really compute a cost-benefit analysis standard method. So at the end of the first year when we're done with testing, if it really doesn't look like it's going to meet the cost-benefit requirements that the military has, we'll stop the project. Slide 32. If we actually do pass that sort of gateway test, we'll be able to go back and do a second year of testing, refine the test procedure, refine some of the software we're using on, and then we can start actually working with our colleagues at Construction Engineering Research Lab, who are our partners in this project, group at Searle, to start developing a new air leakage test protocol. We will be putting together entries for the whole building design guide, a new specification for the Unified Facilities Guide that would be that might go in construction documents for using SonicLQ. We'll be developing our engineering instructions, technical manuals, and then actually a set of case studies for the use of SonicLQ based on the site testing. Slide 33. I already talked about the benefits. This is one of the drawbacks of updating slides. I moved this to the beginning. So we've already gone over the direct benefits of payback and energy savings. Slide 34. So in conclusion, I've talked a bit about SonicLQ that uses sound waves to measure building air leakage. It locates and sizes specific leaks using near-field acoustic holography and looks for overall potential leakage using beamforming. The main benefits here is we have something that's less intrusive and easier to use during different phases of construction than a blower door and IR camera. We're going to be doing testing at Fort Leavenworth and Hill Air Force Base, comparing the blower door camera, developing some new test standards, and the overall potential that we see for energy savings and dollar savings is upwards of $70 million a year to the DoD. Slide 35. Here you can see our webpage and my contact information, and I look forward to answering your questions right now. Thank you.
Thank you so much, Ralph, for a very interesting presentation. I'd like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions on this presentation that Ralph will answer. So for starters, can you give us an idea about how RPMs can get access to SonicLQ and what the associated cost is?
So at this point in time, there is a startup company that's taking the technology from Argonne to finish commercialization. We do not expect it to be on the market for sale for about 12 to 18 months. You can right now actually go and take a look at SonicLQ.com to see the startup company and follow progress. They're going to be our partners as part of this project. They're a subcontract to Argonne on the SERDP ESTCP project we're going to be starting here, or that we have started, but we will be doing the demonstration.
So in terms of timeline, Rolf, when do you expect the technology to be ready for implementation?
So we expect that, yeah, we expect. So we expect the market ready for other people other than people who are going to be pilot testers in 12 to 18 months. That there will be a product on the market. It's going to be, we see that this is going to be a direct sale from the SonicLQ company unless one of the big blower door or infrared manufacturers comes and buys the company up, in which case we don't know exactly what will happen there. But it is not for sale now. And the initial cost is going to probably be about $10,000 an instrument.
Great, thank you so much. This is a question from the National Renewable Energy Lab. For a building that has offices against the exterior walls, does the interior speaker need to be moved from office to office? And then the mic array follows along from the outside?
So if you have a large open office area, the loudspeaker on the inside is providing a fairly uniform low-frequency sound field over a large area. So if you have a big open office, you would move the speaker and probably do something like 20 to 30 feet of outside area at a time with one interior speaker location. You would do that large snapshot. And from beamforming, you move up close, but you don't have to move the interior speaker. It would just be the microphone array on the outside. So so if somebody's from NREL thinking about the RSF user facility there, you would probably have on one of those floors, it's 75, 100 feet long on each of the walls. You might have 10 locations, 5 to 10 locations where the interior speaker would be located, and then you're going on the outside and moving along. So you don't have to have the interior speaker doesn't have to track exactly where the exterior picture is taken. It is a two-person situation, though. You really want to have somebody on the inside and somebody else on the outside.
Thank you. Have you given thought to whether this could be used for a floor system? And is there any way to get around the difficulty of not being able to put a speaker or microphone lab underground?
Actually, yeah. So that's a good question. The ability to look for leaks in a floor assembly is a limitation that you have here, but you have a similar limitation in terms of infrared camera. The blower door, actually not locating, but at least identifying those is the only technology I know. You also would have a very similar situation if you have a lot of leaks into a complicated attic system. So I don't know the answer to that. What you would be able to do is, if you had any idea of where as you go to the underground, where that sound would be coming out. No, actually, I don't see a way that SonicLQ would be able to detect or quantify those. It really is for walls and simple sort of commercial roof assembly systems. A very complicated attic system that has multiple chambers or breaks in between becomes a little bit more difficult to do.
Thank you. Can you please tell us what the air leakage measurement range of this technique is, especially compared to blower door testing? So we have been able to be capturing leaks in terms of crack size here that are pinhole cracks that might be in an air barrier or in a wall, to larger quarter-inch crack size. In terms of the overall leakage rate, that's part of what the demonstration testing here is going to be doing. We don't have those hard limits on the small side when we do a full comparison to a blower door
in a situation of standardized test with a third-party evaluator who's really good at using a blower door. So I can't give you the limitation on how low it can go other than physical size, saying pinhole sizes are detectable, and locating and quantifying that small area, as well as larger cracks that can be as large as your fist.
Thank you.
But in terms of telling you the leakage rate per, in terms of CFM per square foot, I don't know that we've backed those out specifically at what the lower limit and upper limit are.
Thank you. And one last question before we move to Curtis's presentation, and we'll be able to get back to you to answer additional questions at the conclusion of the webinar. How would you perform the testing on tall buildings?
Good. Yeah, actually, that's a good question. For two-story buildings, the microphone array can be put onto an extension wand that you could easily go up 2 stories and possibly even to 3 stories. Anything taller than that, the digital microphone array is actually light enough. We see this as being used with a drone, that a drone would be going around and hovering. And then the question is, how do you get rid of the noise of the drone? The drone should be doing things at higher frequencies than we would be testing with the low-frequency speaker. So we have not actually put it on a drone and tested that. That's one of those things that we hope to be finding a demonstration partner in Chicago who is a commercial building envelope testing company who wants to work with us to try to do some of that testing.
Great. Thank you so much. Again, we'll try and get back to you in the final Q&A, but right now we're going to move on to the next part of this webinar, which will be presented by Mr. Curtis Harrington. Curtis is a senior research engineer at the University of California at Davis in the Western Cooling Efficiency Center. His research focuses on aerosol sealing techniques for remote sealing applications, in addition to climate-appropriate cooling technologies and evaporative cooling. Curtis has developed a patented process for aerosol sealing, detecting, and marking leaks in enclosures. With respect to his background, Curtis earned a bachelor's degree in mechanical engineering from UC Davis and is a registered professional engineer in California. Curtis?
Okay, thank you. Thank you, Rula. So I'm going to talk today about my ESTCP project, Automated Aerosol Sealing of Building Envelopes today, which is just wrapped up, and we've put a draft in of our final report recently. So it's just the end of the project here. Quick agenda. Basically, I'm going to talk today about the project objectives, an overview of the technology, talk about the demonstration results that we've seen, a little bit about the modeled energy savings estimates, and some durability testing results that we did in the laboratory. Okay, so briefly on the benefits of air sealing, Ralph went over this a little bit, but there's significant energy use in buildings related to heating and cooling. It's about 48% of residential energy use and about 35% of commercial energy use. And reducing envelope leakage can reduce HVAC energy use by about 30%, and that's based on a project that National Institute of Standards and Technology performed looking at the impact of envelope sealing in multiple climate zones around the U.S. as well as multiple building types. So the impact is higher in colder climates up north, and it tends to be less in milder climates, but the overall average result was about 30%. Furthermore, the U.S. Army Corps of Engineers recently adopted a tightness standard that's pretty stringent for all DoD facilities, both new construction and major retrofit. So obviously developing cost-effective approaches for sealing these leaks would improve adherence to this code. So for this project, we wanted to demonstrate the new technology for automating the sealing process. Basically, we measured the baseline leakage of the building using standard blower door techniques. We performed the retrofit, and then we did a post-retrofit air leakage test, and that's the primary result for all of these demonstrations. But one of the unique things about this technology is you're able to track the leakage of the building in real time. And I'm going to go over how we do that in a minute when I talk about the technology. So that has an additional benefit. And the overall project objectives we were interested in was to determine the feasibility of doing aerosolized envelope sealing as a retrofit for DoD, develop application protocols for larger buildings. So all the research up to this point has been primarily focused in residential, both single-family and multifamily buildings. So this was our first opportunity to apply this technology in larger buildings as well as in commercial buildings. We wanted to model some energy savings estimates for the DoD and then measure seal durability, because that is something that has come up as a question in the past. So we wanted to do some measurements of that. So briefly on the technology and the concept, you use a blower door on the building to maintain a positive pressure in the space while you apply an aerosol fog of sealant material to the interior. And so as air escapes through leaks in the envelope of the building, the particles are transported to the leak, where they skid out of the airstream and they impact the edge, eventually forming a seal across the entire leak. Because you're using a blower door to facilitate the process, you're able to track the building leakage in real time, so the contractor can watch the building seal and they can decide that the building, they met their target and they can stop the process then, or they can see when the process has stopped sealing any further and they can end it at that point. So with that comes automatic documentation, electronic documentation of the building being sealed. Many times you'd have to have another contractor come in and do like a final audit to measure the envelope leakage, but this process provides that at the end of the process. And finally, it does a really good job of sealing distributed leaks around the building, small distributed leaks that are typically missed by manual methods. This does not seal large catastrophic holes in a building. You'd have to deal with those in using manual or other methods. This does a good job of distributed leakage. So you can see in the photo on the bottom right, there's a bunch of foam sealing that happened in this building, and then you can see right in the middle there's a small gray material. That's the aerosol that found this small spot that the manual methods missed. And so that's kind of the real benefit of this technology is you don't need to know where these leaks are in the building. You just need to know if there's anything catastrophic in the building. Okay, so for this ESTCP project, we've performed several demonstrations. We worked with military bases in Fort Bragg, North Carolina, Quantico, Virginia, and Mechanicsburg Navy Base in Pennsylvania. We did perform the process on primarily non-residential buildings. We also did some apartments as well. But we worked on a school, office buildings, industrial buildings, so multiple building types in this project. Overall, we sealed 15 smaller spaces. These are spaces under 3,000 square feet. And this could have been a space within a building that was cordoned off, so you could compartmentalize a space within the building or a standalone building. We also sealed 3 medium-sized buildings, so that was anything larger than 3,000 square feet. And the largest building that we sealed was 22,000 square feet for this project. Overall, we were able to seal 75,000 CFM at 75 pascals throughout the whole project. So here's some more on the results. We were able to reduce the leakage in all of our demonstrations by about half. That was the average result. The maximum we were able to seal was about 80% in 2 of these demonstrations. And the bar chart on the bottom there shows the overall results of all the demonstrations. 3 of these buildings we were able to bring to within the USACE specification, which we were really encouraged by, considering many of these buildings were in poor condition. They were in some cases scheduled for demolition. So being able to bring some of those buildings to within spec and reduce the envelope leakage as much as we did, we were pretty happy with that. Okay, so now I'm going to talk about a couple of the demonstrations that we performed. This demonstration was in Mechanicsburg. It was an industrial facility. It was an 8,400 square foot industrial site used for training. It took 2 sealing events to seal this building, and overall, we were able to seal 65% of the total leakage in the building in about 4 hours of total injection time. We actually sealed 82% of the available leakage, so that's the leakage after we prepped the building. So this building had lots of roll-up doors, so we had to temporarily cover those and block those for the process, so you're not sealing doors shut. So after you prep the building, we sealed 82% of the available. And this is one of the buildings we were able to bring within spec from 0.672 CFM at 75 pascals per square foot of envelope area down to 0.241. And the USAC's spec is 0.25. The bottom left chart, sealing profile shows you the process as it worked with respect to time and minutes on the bottom. So it started out about 15,000 CFM at 75 pascals, and we were able to reduce that by about 60% down to 6,000 or so in about 2 hours of injection. We had to pack up for the day and come back the next day. We came back, set up our equipment again, and sealed it further from about 7,500 down to 3,000. So over the 2 events, we were able to seal about 65% of the leakage and in a pretty quick amount of time. All right, so the next demonstration I'm going to talk about is the Quantico Elementary School. This is a 6,000 square foot wing of a larger elementary school. It contained 4 classrooms and a hallway that were all sealed. This site was used for our initial training of our subcontractor that we trained on the process. And during that training period, when we set the system up and started spraying, we did not see any impact on leakage. And after further inspection, we found that the roof-to-wall connection had a very significant leak that was not sealed as shown in the plan. So the aerosol was not going to be able to seal this leak, and we had to use supplemental manual methods to try to cover that up in order for the aerosol process to actually do the remaining sealing. So I think that actually is a good approach. In some cases, when you find these leaks, you can do some supplemental manual sealing. But because you're using the aerosol behind it, you can take a little bit less time or care with that manual sealing. You can just block kind of the main leakage and finish it with the aerosol, and it seemed to work really well. So here's kind of a table of the process that was performed, and the bottom figure is a floor plan of the building, so you can follow along with the process. So basically, we did some supplemental manual sealing shown in the red outline around the building, and that was done at the roof-to-wall connection. So we started off with the upper right apartment in shaded in blue, did some manual sealing all the way around. You'll notice that this particular demonstration, we compartmentalized this classroom. So when you seal the classroom relative to the hallway and the other classrooms, there's not a significant energy savings, or if you were to model it, it would show no energy savings doing that. But you do have some other benefits, including reduced sound transfer. As Ralph mentioned, sound transfers through leaks quite well. So if you're able to block those, you can reduce sound transfer, and that seems useful in an elementary school for sure. So we started off at about 6,100 CFM 75 in this classroom, and we were able to drop it by about 80% down to about 1,300 CFM at 75. We moved over to the classroom next to it. The roof-to-wall connection in this part of the building was not as much of an issue, so there was no manual sealing of that. We started the process at about 8,100 CFM 75. We reduced it to 7,300, and we had an equipment failure, so we had to leave for that demonstration and go get the equipment fixed, and we had to come back and finish that. So you see we came back the next month and sealed the rest of the building from 8,100 down to 4,000, sealing about half the leakage. And then we decided to try to seal the remaining part of the building in one try. So we got an extra machine for the sealing, and we were able to seal two classrooms and the hallway all at one time. So when you do that, obviously you're not compartmentalizing between the spaces, so we didn't need to do any manual sealing between the classrooms, and we were able to reduce the leakage from 11,500 CFM at 75 down to 5,800 or so. Okay, and the last demonstration I'm going to talk about today is a 3,000 square foot office building. This demonstration was performed at the time of tenant changeover, so this building was going to be reoccupied shortly after, and so we had to take extra care with the floor. So this aerosol product will fall onto the floor or any horizontal surfaces, so you need to protect those surfaces with plastic and tape. It doesn't adhere to walls or anything because there's not a velocity or impact made to that wall, so it really just falls out onto horizontal surfaces. To prep this building, it took about 16 person-hours of preparation, which is about a 2-person team, about 1 day of work. And then we started sealing, and we were able to seal about 80% of the overall leakage. It went from 4,500 CFM at 75 pascals down to below 1,000. And this, again, brought this building to within the USACE spec from 0.493 down to 0.158 CFM 75 per square foot. And this took place in only 3 hours of injection. So there was some significant preparation required, but the sealing time is actually quite short. And the building operator was really pleased with the overall result, and they want to seek lead credits for this effort. So we were happy about that. The bottom left photo is a good photo showing some contrasted images of the sealant. This is a black room, and the gray sealant at all the seams show where the seals are applied through the aerosol, and it looks like someone came through with a caulking gun and just sealed up all of those walls. Okay, moving on to some of the modeling that we did. We took a DOE reference model in Energy Plus, and we modified the infiltration model based on PNNL's infiltration guidelines, and we applied a 62.1 ventilation guideline. So normally the reference models use a standard exchange rate with outdoor air. This model we modified so that we're using wind-driven infiltration and natural effects driving infiltration. We simulated this building in 4 climate zones in California, in Georgia, North Dakota, and Texas, and we looked at 2 different leakage levels. So the baseline leakage that we used was based on the NIST database for commercial building envelope leakage around the U.S., and the tighter building was based on the USACE specification. It was a pre-1980 built building. It was 5,500 square feet office building. And what we found was that there's some significant heating energy savings when you seal the envelope. So we saw at least 30% heating energy savings and up to 45% in some climate zones. What you'll also notice is that cooling energy savings was mixed. So in some cases you actually saved a little bit of cooling, and in some cases you used a little bit more energy for cooling. And that basically comes down to the climate zone. So in the more humid climates like Georgia and Texas, where you have lots of humidity outside, you end up taking a little bit of a penalty, or actually you get a benefit from sealing the envelope. But in drier climates like California and in the cool, dry North Dakota climate, extra infiltration into the building actually helps reduce the cooling load because there's a lot of cooling hours when outside air is cooler than inside air. So infiltration in those cases actually helped the cooling load in those buildings. So there's also a little bit of fan energy savings. It looks like this plot didn't come in very clear, but in Fort Benning there was also some fan energy savings. That's basically just reduced fan energy because there's less heating requirements for the building. Okay, and lastly I'm going to talk about some of the durability testing that we performed. We basically sealed a bunch of test plates in our laboratory using the aerosol process, but we applied it under different humidity conditions. So this isn't outside humidity, this is the humidity target that we controlled our machine to on the interior of the building. So applying that at different RH, at different humidity levels allows us to create different qualities of seal. And we performed 4 different tests. We performed pressure cycling at 1,000 pressure cycles at 800 pascals. We also performed this test at 100 pascals for even more than 1,000 cycles. We did what we called a hurricane test, which was 1,500 pascals maintained for an hour, and this essentially is about a 100-mile-an-hour wind speed on one of the building leaks. And then finally we did some temperature cycling, 1,000 cycles between 80 degrees and 120 degrees while maintaining the seals at 800 pascals across. So the overall results are shown here. What we found with our 800 or 1,000 cycles at 800 pascals is there was no significant change in seal tightness. There was a gradual drift in leakage over the entire time of the testing, and it's shown here in the data on the right. It shows in blue the first 100 cycles, the average leakage of the first 100 cycles, and in red was the average leakage of the last 100 cycles. So you can see in some cases there was, or in most cases, there was a slight increase there, but it was pretty minimal. And then in sample 3, we had a malfunction with our controls on the apparatus that we were using, which overpressurized that seal to 4,000 pascals. And that tended to kind of increase that leakage. It didn't have an abrupt failure like we noticed when we did a manual seal puncture using a physical puncture of the seal. You could see that clearly. This was all gradual. And we actually didn't see a leakage plateau, so it seemed to just slowly rise over time. And so we wanted to investigate this further by applying a more realistic building pressure of 100 pascals, which is more realistic than 800 pascals. So when we performed the 100 pascal cycling, we have more than 1,600 cycles at this point. I think it's up to 1,900 right now. And we observed very minimal, if any, drift in leakage. The data shown below shows a pretty flat line, demonstrating that these seals that are performed can withstand pressure and are pretty durable. All right, and so the major conclusions of this project is aerosol sealing seems to be an effective method for sealing buildings. We're able to seal buildings relatively tight and pretty efficiently. It also appears to be most appropriate during time of tenant changeover. We don't currently envision this being used when there's computers and desks and things in the space. While it's conceivable you could cover those with tarps and things, at this stage of the technology it just doesn't seem really appropriate for that type of building. So any time of tenant changeover, obviously new construction, this has worked very well for us in other research as well. So those are the primary times to apply this. We also found that through our modeling that the USAC tightness level can minimize infiltration. I forgot to mention this before, but buildings that require some type of pressurization target really require more air to pressurize the building than is required for ventilation. So that's an additional energy benefit. If the building has a pressurization target that you're trying to meet, you can reduce the amount of air required for pressurization down to basically the minimum ventilation rate. And the tightness level that USACE has specified is enough that that ventilation is going to pressurize that building by itself without additional outdoor air. And then finally, seals have been shown to withstand pressures beyond what a building would normally experience, demonstrating its durability. So that's the end of the presentation, and I'd be happy to take some questions if anyone has any questions.
Yes, thank you so much, Curtis. We have received a number of questions on your presentation. So let's go ahead and get started here. How do you keep the aerosol from depositing on walls, floors, and equipment?
Sure. Okay, so I mentioned this briefly. We do have to cover horizontal surfaces for an occupied building. If you're going to do a major renovation, that's a kind of an obvious time to apply this. If you're going to replace the flooring in a building, things will be removed. You know, if you're going to replace carpet or something like that, this would be a great time to apply this technology because you wouldn't have to worry about the floors. And that's very similar to like a new construction type scenario. But in tenant changeover, when you're not doing a bunch of tenant improvements, you do have to cover horizontal surfaces because the particles fall out due to gravity. But they will not adhere to walls because the particles really need some momentum and impact to actually stick to the surfaces. So there's only near leaks is there enough velocity and momentum to get those particles to stick. They don't stick to vertical surfaces.
Thank you. This is a question from Oak Ridge National Laboratory. Can you tell us a bit about which infiltration method you used in your simulations? Was it something like design flow rate or flow coefficient? And also, what was your infiltration schedule when the HVAC was on?
Okay, those are good questions. So the infiltration model basically was based on PNNL's infiltration guidelines, and so it uses only wind speed. It does not take into account temperature difference, so this did not simulate stack effect in these buildings, but it did have a coefficient to associate wind speed to infiltration. The schedule, they do recommend having a reduced infiltration schedule during occupied hours or when the mechanical systems are running. And that's because buildings are assumed to be slightly pressurized, at least commercial buildings. And from our research and looking at kind of in our baseline leakage for our model, we found that even the ventilation air, if there was no exhaust in the building, there's really no pressurization in these buildings because there's too much leakage. So we did not apply any kind of correction during occupied hours for the baseline building. For the retrofitted building, because the ventilation does pressurize the space significantly just due to the outdoor ventilation requirement, we assumed that the infiltration was reduced to 0.
Wonderful. Thank you so much. Can you please tell us what material you used for the aerosol sealing?
Sure. So the material is a acrylic polymer that is used for exterior applied air barriers. It's normally spray. It's a commercial product that we've modified slightly by diluting, and the company that has licensed the technology is working on modifying it even a little bit more. But essentially, it's an acrylic-based sealant that has been watered down.
Thank you so much. Can you tell us how you address leaks above suspended ceilings?
Okay, so if there is a drop ceiling or a suspended ceiling, it's not clear to me that that the air barrier should be applied at the drop ceiling. In some cases, I understand that people do want the air barrier at the drop ceiling, but generally, in this project at least, we removed ceiling tiles to address leakage above the ceiling tiles. So you would in most cases probably want to remove those ceiling tiles. For one, they won't hold pressure very well, but also if you're going to seal that and then someone opens those tiles, it's going to damage those seals that you formed. So it's probably best to deal with leaks further out towards the exterior envelope. And so we would remove tiles in that case.
Thank you. What is the tightest you have sealed a building with your technology?
Yeah, so in general, we've seen about 80% of the leakage sealed is kind of the average that we've seen, and we've gotten really small apartments down to 0.16 air changes per hour, which is really extremely tight and unnecessarily tight probably. So the limit is quite low.
Thank you. And how large of a leak can the aerosol seal?
So the aerosol can seal leaks up to a ½ inch or more. There's no technical kind of reason it couldn't seal larger leaks. It's just a practical one. It takes longer to seal larger leaks. It goes with the square of the size of the leak. So every time you double the size of the leak, it takes 4 times longer to seal that leak. So it seals leaks like 1/8 inch and 1/4 inch much more efficiently than ½ inch. Although we've seen leaks as big as ½ inch get sealed in the past.
Thank you. And one last question before we open it up to broader questions to both you and Ralph. Can you tell us if your proposed process, can it be performed with contents in the space that you are trying to seal?
Yeah, so that's It's possible, and we've done it in the past. Although we did find some issues with that installation. So at this point we wouldn't recommend doing it with content in the space. It'd be best to remove those contents from the space.
Excellent. All right, so we're going to wrap up with questions with both you, Rolf and Curtis. So,
okay.
So can you please each summarize what one should consider before sealing a building? And if you don't mind starting, Rolf, before we turn it over to Curtis.
Okay, so I would say he's actually going to give a better answer than me, given that he's actually doing the sealing. So I'm working on the detection side, but I think the considerations before sealing a building are just understanding what are your goals to be setting out. Are you sealing this for energy purposes? Are you sealing this for air quality purposes? Are you sealing this because you're worried about moisture transfer through the envelope? Are you sealing for CBR attacks? Because each of those has a different set of needs and prioritization as to how you're going to attack the problem. I mean, I guess in all cases you want to hit the biggest leaks first, but if it's a matter of trying to seal up to meet US ACE requirements, understanding where the big leaks are and being able to prioritize as you go down the list, I think, is important. And one of the other things here in terms of the sealing is how are you planning, when are you planning on doing this? As Curtis had just explained, he thinks that his technology, as incredibly awesome as it is, isn't as useful when you have an occupied building. So you have to be looking for an opportunity when you'd be doing a major retrofit, or we're putting in flooring, or we're putting in new ceilings, so we've taken all the pieces of equipment out. And if you are going to be using more manual methods, you might not have to go through those steps. It's just going to probably take you longer to do much of the sealing.
Curtis?
Yeah, and I would say you definitely need to look at what type of ventilation system is applied. So in especially like some of the apartments we've sealed in the past, many residential buildings are exhaust ventilated primarily or solely. And so if you start to seal buildings to really tight levels, those systems aren't going to work very well. So I would look at the ventilation systems that are installed, especially if you're trying to get better air quality in the building by sealing envelope leaks. You should think about how the ventilation is distributed in the space. You could also consider if you are trying to reduce energy use in a building, that your systems might be oversized after sealing. So it may be part of a larger retrofit that you want to perform, and so you should consider the fact that air sealing would reduce the load in the building and allow you to downsize some of that equipment, saving even more energy in the future.
Thank you both. In which climates does it make the most sense to use these technologies? Are they useful everywhere? Rolf, can you please start?
So yeah, actually you just saw in Curtis's slides, there was a really good set of slides showing the differences when he did this in Miami, or is it Texas? Yeah, I guess you had Texas, Georgia, Atlanta, yeah, and North Dakota, and when you have a heating climate where you have most of your energy, if you looked at the building, goes into heating, you have good outside or low outside air temperatures, you're going to have a bigger benefit than something that's a temperate climate, like a San Francisco. You tend, as you saw from Curtis's slides, on cooling, it depends upon a lot on whether you're a dry climate or a humid climate, if you're going to get an energy savings or not. So in general, the idea of using sealing for energy saving is going to be predominantly where you're heating dominated. So the ASHRAE climate zones 4, 5, 6, 7, and up are the ones that really have the most, I think, the most benefit. And this can really be quickly put together with a simple energy model to go ahead and say, all right, let me take a baseline, the commercial energy model that Curtis had used, reference building, and change that infiltration and see how do I have a change in my heating energy and cooling energy. You may not get the exact right number of your energy savings, but we'll tell you, oh, am I going to get an energy savings from cooling? Am I going to get an energy savings in heating? Curtis?
Yeah, that's a great response. I guess in terms of the technology itself for the aerosol process, there are abilities to precondition the air with the technology. There's heaters that we use on the blower door air. So if the temperature gets too low outside, and we haven't tested in like sub-freezing temperatures in the past, there could be issues with applying the technology, but there should be some ability to precondition that air with heat, allowing you to perform in humid climates as well as very cold climates, at least with the aerosol process, because it does rely on some evaporation of that aerosol fog in order for the particles to be distributed around the building. So we've tried to mitigate and allow the largest or most flexibility with respect to climate zones, but we haven't necessarily tested in very cold climates. In some of the tests for DoD, we were applying this in 100% humidity conditions because it was downpouring rain, and with the heat that we added, we were able to still perform the process effectively. So that's a different angle on the question, just with respect to the aerosol technology.
Great, thank you both. And then as we wrap up here, what is the final takeaway message you would like to leave our audience with today? Ralph?
So I guess I'd like you to take away that there's research and development and hopefully a positive demonstration in this ESTCP with SonicLQ for a new technique for measuring leakage in buildings that should make it easier for you to both locate and size. It really is applicable in that case to existing buildings as well as being used for quality assurance, quality control during construction of new buildings that we know are going to have to be tight. But to make sure that you're going to be able to pass the blower door test and not have to call in Curtis to seal up the leaks that you should have caught when you were putting together the building to begin with.
Thank you. And Curtis?
I guess I think this technology is new to a lot of people, the aerosol sealing process. And I guess I'd like people to recognize that it works quite well and efficiently, and there are opportunities to use it in lots of situations where buildings are being changing a tenant or going through a renovation, and it's much more effective than lots of manual sealing techniques that are used today. It doesn't rely on knowing where the leaks are, so it really takes that kind of out of the picture and allows a very effective way of sealing buildings. There are some considerations, and because people aren't familiar with it, they may have some questions about it, and so I hope that people would reach out and ask those questions to get more comfortable with the technology, because it has been recently commercialized, and we expect it to be, or is being sold in new construction currently for residential, and I see it going to commercial buildings and retrofits shortly. So just understanding that it's out there and being familiar with it.
Wonderful. Thank you so much. I'd like to thank you on behalf of all of us here for a very informative webinar, and I'd like to remind our audience that the next webinar in the SERDP and ESTCP webinar series is on Thursday, December 7th, and it's titled Management of Novel Hawaiian Ecosystems. This webinar will feature Dr. Susan Cordell from the United States Department of Agriculture Forest Service and Dr. Rebecca Ostertag at the University of Hawaii at Hilo. Registration is already open for this webinar, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a moment of your very busy day to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you.